what's been the impact of OpenDSS or EPRI and outside EPRI. On the other hand, Florent is going to talk about modeling the French power distribution grid from open data sources. How and why. And with this, we want to provide an overview on how, through our experience, we see open source tools as a pillar for keep moving the power industry forward. And with that, let's get started. Let's talk about the open source tools at EPRI. How do we use them? Why our interest on them? Well, these questions require probably an introduction to who we are and what do we do. At EPRI, we are a private non-profit research institute that has been leading the electric power industry for more than 50 years. At EPRI, trusted experts collaborate with more than 450 companies in 45 countries, driving innovation to ensure the public has clean, safe, reliable, affordable, and equitable access to electricity across the globe. Under the slogan, Together Shaping the Future of Energy, we propose to the industry the next steps for moving the energy business forward without leaving behind utilities, stakeholders, and customers. The product of EPRI is the technology and intellectual property that, depending on the scope, is distributed across our members or openly to the public. And an interesting case is OpenDSS. OpenDSS was born as DSS back in 1997 from the hands of Roger Dugan at Electrotech Concepts. It was a private product for supporting distributed resource integration and grid modernization efforts. Then, with Tom McDermott, they added many new capabilities to support the smart grid analysis, including a wide number of device models and simulation modes for this purpose. The simulation platform was originally built for execution in a single sequential process. Each procedure or function is called sequentially to perform a QSTS simulation. The performance that can be achieved with that structure was based on the structure of the low-level routines, the simplicity of the routines, and the efficiency of the compiler. Then these people, the team that was working on Electrotech Concepts, moved and was hired by EPRI. And at EPRI made the program open source in 2008. This to encourage efforts in grid modernization by providing a tool to the power industry capable of performing advanced studies. The program's name was changed to OpenDSS to emphasize that it was open source. The OpenDSS is a general-purpose frequency domain simulation engine that has special features for creating models of electric power distribution systems and performing many types of analysis related to distribution planning and power quality. It does not perform electromagnetic transients, which means time domain simulations, and all type of analysis is currently in the frequency domain. For example, let's talk about sinusoidal steady state. However, it's not limited to 60 Hertz. It does perform electromechanical transients and dynamic analysis. The program heritage is closer to a harmonic flow analysis program, or even a dynamics program, a typical power flow program. This may seem a strange place to start designing a tool that will end used mostly for power flow studies, but it gives the tool great modeling flexibility, particularly for accommodating a wide range of load models and unusual circuit configurations. It is easier to make harmonics flow simulation program to solve the power flow problem than the opposite, and I'm citing Roger Dugan talking about it. Then in 2013, Roger found this interesting paper on the internet that was talking about real-time simulation based on frequency domain simulators. And there was a special case in which this guy in 2013 was using OpenDSS to perform real-time simulation. That guy was me. So we met, we got together, I introduced him to the products and techniques that we were using back then. By that time, OpenDSS only came with two interfaces, the executable, which is the GUI that comes naturally with the program, and the COM interface that was a very good, and it is nowadays an interesting interface for Windows users in which they can interconnect their programming language with OpenDSS through a common object model. But it was insufficient back in the day because we had to do some special operations a bit faster than using late binding with the COM interface. And our programming language didn't support early binding, so we had to find a better way to do things. So we created the direct DLL, and we use it for performing our real-time simulations. So people got very excited at EPRI. I joined them in 2015 for an internship, and then I was hired in 2016. And since then, we've been adding more and more capabilities to OpenDSS. We introduced the parallel processing suite within OpenDSS. We now distribute the program with 3 interfaces: the executable, the COM interface for Windows users, and the direct DLL, which has been the base for many developments across platforms like Linux and Mac, given that the structure of the DLL mimics better a shared library that can be easily replicated into different operating systems. We also have been adding new models that have been requested for the projects that we develop at EPRI, adding more capabilities for moving faster, more products derived from OpenDSS like OpenDSS-G, like visualization tools like OpenDSS GIS, so we can take the data that we have in our models to different platforms, visualization platforms, for allow us to present better test cases, better study cases to our members, and facilitate the way we communicate with our members, widely. We have been also working for the last year in translating the native language in which OpenDSS has been written into C++, giving a project that was requiring us to do that. This in order to keep expanding the number of not only users but also developers that want to keep cooperating with us and want to keep using OpenDSS as the main core for keep developing new products, keep increasing productivity in many ways, testing cases, proposing ideas, having a very interaction with vendors, proposing new models and technologies that could help moving the electric power industry forward. So as you can see, it's been a long way to get here, and more things are definitely coming in. We expect that we're going to keep developing the tool, and the experience has been great. So now let's talk about the impact that OpenDSS has outside. How can we measure what's been the impact out there, not only on the industry, which is basically a feedback that we get directly from our members, but how OpenDSS has been impacting all other areas like academia, research, and many others. So if we go to the IEEE Explorer library, we just enter the word OpenDSS, and we're going to find more than 459 results for the word OpenDSS. This picture was taken on the 4th of May, May the 4th, of course. And as you can see, we have a lot of citations. Not only citations, but the name OpenDSS included in the title of the paper. Of course, not only our papers, but many papers in the academia, people proposing new methodologies, proposing new models, proposing new capabilities for the distribution grid, and all of them are using OpenDSS to reach out to their goals and to present results and start conversations with utilities and with other colleagues around the same topic and presenting results, which is a very powerful advantage of using OpenDSS. Also, we can count the number of downloads that we have since 2008. So far, we have 158,000 downloads of the program reported at the repository of OpenDSS at SourceForge. And it is expected to keep going up because every day we hear about someone else developing something based on OpenDSS, proposing new ways to perform analysis, and using OpenDSS as the base of the analysis, as the base of the prototype they're trying to develop to present a strong case and start a conversation about a particular topic. So based on this, at EPRI, we have different areas in which we can catalog and categorize the way OpenDSS has been beneficial for us. So it's a simulation platform that we can use for contrasting and conducting studies. We can help debugging and understanding better methods and obtaining results that will allow us to compare to other vendors and other software, to other packages out there that will give us the freedom to propose prototypes, supporting demonstration, new practices, trends, etc. OpenDSS has been a great foundation for new tool development. This for covering our members' needs and without having to wait for software vendors to find a reason, a good motivation to move forward and start the implementations. Instead, we can provide prototypes to the members so they can have a better communication with software vendors to request what is needed and have proof on how it will impact their business. It allows us also to facilitate the communication across the industry. We have a better communication with our members, which are the utilities, enables discussion with software vendors so we can evaluate how these capabilities that we are developing can be adopted by them and vice versa. Provides a platform for discussing with the industry and academia what's the next step or what are the next steps in the power system analysis. And also, finally, it's a perfect tool a perfect vehicle for communicating our developments not only to members but also to society. And we have several products that are product of that. For example, we have Drive, which is the hosting capacity analysis that now has been adopted by several software vendors. We have Adapt, which is the planning tool that we are currently using for integrating non-wireless alternatives. OpenDSS-G, which is a freeware software tool that will allow people to operate OpenDSS in a graphical way, not only scripting. GIC Harm for different analysis, and so on. I just wanted to mention these four, which are kind of the most popular. We have a large number of applications that are based on OpenDSS and allow us to answer to the questions that are proposed by our members. And outside OpenDSS, we have other initiatives. For example, we have packages for analyzing PV, for analyzing optimal power flow. We have initiatives like Zendi that has OpenDSS in the cloud for allowing users to perform microgrid studies, microgrid analysis. And we have some others in a very low level kind of based on Python that are extensions that some users have developed to extend the reach and the current state of the art of OpenDSS, and everything based on this very interesting platform that allow us to communicate to everyone. So as you can see, OpenDSS has been great for communicating not only the results that we do at EPRI, but also to create community across and keep moving the energy business forward. Thank you.
Okay, thanks for watching the video. And Davis wanted to apologize for not being here today. He's actually in Montreal, Canada for another conference, other French-speaking place, but not exactly next door. If you have any questions, feel free to forward them to Davis, of course. And I'll switch to my own presentation. Okay. So my name is Florent Cadoux. I am the CEO of Roseau Technologies. We are a software startup based in France, in the southeast of France, in the city of Grenoble, in the Alps. And today I'm going to talk about open data, not actually open source software, but open data that describes the power distribution grid in France and what can be done with it. I'll show an example of an application that basically consists in doing some electrical model based on open data. So electrical model means being able to determine power flows, voltage, currents, etc. in the grid solely based on data that's publicly available. First, some general information about the French power distribution landscape. So we have nearly 1.5 million of kilometers of distribution network, medium and low voltage. It's a huge infrastructure, obviously. It's a public infrastructure, which I think is important in the context of open data, because it means that it makes sense that the data that describes this public infrastructure is also public. But it's operated by DSOs, distribution system operators, which are not, I mean, they're private companies most of the time, but they're only operating the grid. They don't own the grid. And we have one vastly dominant DSO, which is called Enedis, and they operate all the blue area on the map. And then on the green area, we have 100 plus smaller local DSOs that do the same job, but on a separate geographical area. Now let's come to open data. So the regulatory context is very important because I think that's what fueled the development of open data in France. And as you will see, there's a lot of data that's publicly available in France, more than in other countries. And that's thanks to the regulatory context. So there was a first law in 2015, which was specific to the energy sector that mandated the publication of energy data, not grid, energy, how much electricity is produced and consumed. And then in 2016, there was another law which was much more general that mandated open data by default for all administrations, from the central state to the local city councils, and even including for companies, public or private, that are in charge of a public service. So it's very, very general. And that includes distribution grid operators, which means that since 2016, DSOs had to share a lot more data than they used to, which is why they created in 2017 the ORE agency, which is an association of DSOs. And the idea was that because they had to share the same data by law, they would create a single platform where all the DSOs would put their data and users could find the data all in one place. So if you, that's what happened. And in 2018, this ORE agency published they launched their website. And if you go to their website today, we'll find something like this. So we'll have a list of tens of data sets that describe the distribution grids for electricity and gas also, by the way, in substantial details. So this all looks perfect and simple and nicely designed. There's a few caveats that make things a bit messier than what I just described. So the first one is that the transmission system operators had the same obligations. So they also came up with their own website, which is called Audrey on the left, not ORE, which also shares data. And of course, because the transmission and distribution grid partly overlap, the data also overlaps, which means that these two websites actually provide some redundant information. And of course, redundancy means potential inconsistencies. Then the DSOs, not all of them, but the largest ones, decided that they wanted to keep their own open data websites as well. And of course, the data that they share here is also somewhat redundant with the one that they put together in the shared ORE agency website. Then the French government did the same thing. They have their own open data website with plenty of information, including grid data. And all of this is partly redundant. And then you have OpenStreetMap, which is very separate because everything I've mentioned before, I mean, there's different databases, but the data originates from DSOs. The DSOs produce the data, they put it on their own website, they send it to other websites. On the right, OpenStreetMap, the data is crowdsourced, so it's completely separate from the data on the left. And that's the complete landscape of all the data sets that we have about distribution within France. Now let's see what data we can find in those data sets. Regarding the infrastructure, you can find substations, primary and secondary. You can find lines, and you know whether they are medium voltage or low voltage. And you know also if they are underground or overhead. That's what you have. Regarding loads, we have energy estimates, not power. Power would be more meaningful for power flow studies, for instance, but we have energy. And the energy estimates are aggregated essentially by village. It's called the IRIS unit, but anyway, it's like 2,000 people grouped together. Let's call that a village. Generation, same thing. We have a list of generators, but they are also grouped, aggregated by this IRIS unit, let's say village. And that's all we have and that we can use for modeling the grid. Then let's look at what we don't have and wish we had for doing power flow analysis. So first, regarding the infrastructure, we don't have the physical characteristics of lines. We don't know if they are copper or aluminum. We don't know if the cross-section is small or large. We don't have much information either about transformers. and switches. And switches are important because they determine the topology of the grid. So we don't know any of this. Regarding the loads, we don't know anything about the phase connection for single phase customers in low voltage grids. And obviously we don't have any detailed information about individual loads. For generation is the same. We don't have the precise location. So we know roughly where the generator is on a certain area. And lastly, everything on the top describes the infrastructure, but even if we had perfect information about the infrastructure itself, we would still need some additional information regarding how the infrastructure is operated. And that means basically two things: switches settings, which switches are open or closed. Obviously, we don't know where the switches are, so we don't know either whether they are closed or open. And also transformer settings. The ratio by which a transformer transforms voltage can be adjusted, and that's also something that we don't have. If we had all of this, we would have perfect information for running a power flow calculation. A few more comments before I go into the application. The first one is about data integration, in the sense that we have over 100 DSOs and we want to integrate the information from all of them. The good news is obviously that because we have one super large DSO, it's fairly easy if you want to process grid data, it's fairly easy to do it over 95% of the grid, because there's just one DSO. The bad news is that, it looks that you could easily go to 100% because all the data is in one place in this ORE agency website. But actually, if you take a closer look, you will realize that even though the data is all in one place, there are still substantial differences in the way each DSO stores their data into this single database, which means that actually you still need to do some custom work if you want to process the data from various DSOs, unfortunately. But still, it's quite easy to get 95%. Now, one more comment about data quality. The first one I've suggested before, because we have data in several places and it's redundant, there's a risk for inconsistencies. I'm going to give you what I think is the most prominent example: primary substations. Primary substations is what makes the interface between the transmission and the distribution grids. And one question we could ask is, how many do we have? Fairly simple question. And we could ask the question over the Enedis territory, so the blue area, and over the whole French territory. Now, for the Enedis territory, if you look at the website, the Enedis website, so the DSOs themselves, on their open data portal, you will find a list of 2,935 primary substations. But if you look at the ORE website, so the website where all the DSOs put together the data, and the data was also provided by Enedis there, of course, you will only find a list of 2,240 primary substations. And if you look at the entire French territory, blue and green areas, the Audrey website, so the website of TSOs, will provide you a list of 4,000 primary substations, and the ORE website, DSOs, only 2,000 something. Now, for those of you who may not be familiar with electrical engineering, this is what a primary substation looks like. So you would think that we know whether we have 2,000 or 4,000 of those things, right? But if you look at the data, it's not so clear. Updates, they tend to be quite irregular. And also, as in any data set, I guess, there's inconsistencies between the data set and the reality on the ground. I guess that's unavoidable, but it tends to be maybe stronger in distribution grids than in other data sets. Okay. I've shown you the data sets we have, what data we can find in them, which data we don't have. All the aspects regarding data integration, quality, and so on. Now let's actually do something with the data. What we want to do is build the electrical model, and there's essentially two steps. The first one is geometric. The lines and transformers and so on are just a collection of individual points and lines, and you want to process that to recreate a grid. So you need to find the topology, the logical topology, which element is connected to which. And that's essentially a geometric problem. And once you've done this, you need to add all the information we don't have, and you have to guess. So, of course, it's educated guesses. So when you know a little bit of how grids are designed, you can assume that if this line is a medium voltage line underground, just coming out of a primary substation, it's probably going to be this type of conductor, and for every question you have, you do this and you guess, and you end up with a usable model. Now, of course, because some of the information was guessed, there's a strong question about the model validation, and that's something I don't have enough time to discuss today, but if you're interested, you can do it after the presentation. We have ways to compare the quality of the model done this way with what's done when you actually have all the missing information. Let's turn to an application. There are several, but I'm going to show you the most prominent application we have, which is a web app for simulating the connection of renewable energy projects. So the idea is that you go into the app. So let's say you're a project developer. You find a field somewhere where you can do 3 megawatts of PV. And you want to know whether the grid connection will be costly or not. And that's very important, because if it's costly, you don't want to put more time into studying the project. You want to get rid of it immediately and not waste time on it. And conversely, if the grid connection is not too expensive and the project will be economically viable, then you want to secure the project as fast as possible. So it's an important question. And this app makes it possible to do the study basically in 3 minutes in a web app very easily, compared to asking the DSOs, which in France takes 3 months, costs 5,000 euros every time you ask a question, and provides an answer which is not transparent, in the sense that you won't have access as a customer to which assumptions the DSOs made when doing their study. And this transparency part, I think, is the most important of all, actually. So this type of app is not very original. You will find many DSOs offering this type of, they call it self-care or self-serve apps that does exactly this. So the idea of the app is not original. What's original, I think, is that I don't know any other example where this was done based on open data. And I think it's very important, again, mostly for this argument of transparency. So just 3 more take-home messages. So the first one is that we're lucky enough in France to have a very rich data set about power grids. I mean, we've looked at other countries, and I don't think there are many examples where you can find so much data about grids publicly. So it's a nice playground for anyone who wants to experiment with grid data. The second is that even though we have a lot of data, there's still a lot of things that could be improved regarding this data, its quality, etc., etc. And the last thing is that doing this electrical model based on open data was not, let's say, theoretical exercise. It actually proved very useful for renewable energy project developers, as I've shown you. And we have other applications as academic researchers doing their research based on this. It's been a problem for decades. I mean, in academia, people have been working with the same 10 grid model for 20 years because they don't have more data. And also for public authorities, so people regulate power distribution. And we also have examples where those type of players use the data that we have put together with this approach. So it's actually, it proves very useful. I'll stop there, and feel free to ask any questions. Thank you. Yes?
Did you manage to, or at least create like some conversation with the DSOs or TSOs, or at least did they indicate an interest to consolidate their data at all? Since like from what you saw shown, it's like very, very divergent.
I wouldn't say very, yeah, for primary substations, like 4,000 or 2,000, it's like ridiculous, but there are reasons behind this. I think they're not putting the same meaning behind primary substations. So this example I shown is the most, I think, it's the worst divergence. Other than that, no, we haven't tried to ask them to communicate more. I think they know what they have to do, right? And also, we don't use TSO data that much. We really focus on DSO data. So we try to get the best of all the distribution grid data we have. And when it's not consistent, we have rules for trying to make something that's the most plausible. And again, validation is key here. So we did what we could to make sense of the data, even if it's not consistent. And then we compared. So there's 2 ways to do this basically. The first one is when you have, on some areas, we actually have the real grid data, and this is because the grid are owned by municipalities, and because they own the grid, they have the data. So if you go talk to a municipality, sometimes they can let you do stuff with the actual data. Second thing is the renewable project developers, they get quotes from the DSO when they want to connect to the grid, and those quotes contain also data. And what you can do is check whether you were able to accurately forecast basically what the DSO would answer when you ask them for a quote. So the two ways to check, and it's not too bad. Yes?
So first question is like the dataset you compiled, is that open and cannot be accessed? And the second question is what other use cases apart from the interconnection use case do you see with having open grid data?
So the data we compiled is not open per se. We have shared a little bit of it, but not the entire French model, which is huge, by the way. What we do, we share the data with academia, and so some researchers have access to it, but they ask us and we provide it. It's not like open. But when people someone wants to use it for a non-commercial purpose, we do it. And the reason we keep it closed is because we actually make money out of it by selling this to project developers. So if we made it available, there would be a risk that we cut our own source of revenue. So that's what, we provide it on an individual basis for non-commercial users. And now the other part of the question was the application. So I can elaborate a bit more on what I suggested. So for research, it's very important to have grid data. Whenever, let's say you want to do some cost-benefit analysis for whatever new smart grid solution. Let's say flexibility. Everybody speaks about flexibility. You have one specific implementation of flexibility, and you want to check its technical economic value. And that's very important, by the way, because I think that's one of the reasons why some DSOs, at least, are opposing flexibility, because they think there is no economic value into it. Maybe not any form of flexibility, but let's say low voltage flexibility, which is something we also work on. It's completely separate from what I've shown today. Few DSOs think that there is some value in low voltage flexibility, as far as I know. Let's say you're a researcher and you want to investigate that. The way to do it is to take a large number of low voltage networks, simulate what would happen over the next 30 years when you have or don't have this new technology, and you check whether you are able to defer or avoid completely some amount of capex investments. Okay, well, you can only do this if you have low voltage grid data. And before we did this, it was impossible. If you go see the DSO and ask for data, we say, no, it's private data. We can't share it. So for research, I think it's really interesting. And then for public authorities, I think it's very important as well, because maybe it's specific to France, but when so again, the grid belongs to the municipalities. What the DSOs are saying is, okay, you own the grid, but we generate the data as a DSO. We are the ones who do the work. When we add a transformer, we take notes, and the data is generated by us. So even though you own the grid, you don't own the data. The data is ours. So we will share it with you, some of it, not all of it, and the data we share with you can only be used to do this and this and this. I'm not sure how legal or meaningful this is, but that's the way it works. And because of this, municipalities only have a limited access to information, and they can't do what they want with information. Now, with this approach, you get a model that's completely free of use. And so for some applications where the municipalities cannot legally do something with the data they get directly from the DSO, sometimes they can do that thing indirectly using the open data. So I think it's important as well for checking on what the DSOs are doing from the regulatory viewpoint. I think we're out of time, or nearly out of time, so maybe we can stop there, and if you have more questions, we can discuss after the break. Thank you. Ah oui.
J'ai travaillé là-bas, j'ai fait des gros modèles avec.
Ah oui. Non, ça...
Même en interne, on a du mal à les avoir. Hein.
Ah oui, bah oui, justement, en fait,